Right, so in this session we'll be solving some problems related to functional groups. As you see, there are four different compounds, each containing different kind of functional groups. So the first one, if you just look at this compound and if you just focus on this area, that functional group is an ester functional group because you have a carbon double bond to oxygen with oxygen linked to the next carbon. So that's an ester. If you come here with the heteroatom nitrogen, the nitrogen has two metal groups attached to it, and that would be qualified as an amine functional group. Actually, from our discussion, this would be a tertiary amine functional group. The rest are usually, this is a phenyl group, this is a benzyl group. If you in the future will see this is just a phenyl, and with one more carbon to this carbon, this is called benzyl. These are not actually now interesting in terms of functional groups, but I want to remind you, just a single phenyl group attached to a carbon is phenyl, with one more carbon is benzyl. But the most important functional groups are the ester group here, R, C, O, R. If you just consider this whole thing as R, this would be R, C, O, O, R. So the general formula looks like this, R being this ethyl group and R prime is this whole thing after the oxygen. So that is the functional group. If we consider the next compound here, if you just outline this right there, that is an R, CO, NH group. So if you have RCONH, this is an amide functional group. Not amine, but amide. And here you have RCOOH, which is an acid. This is R group attached to COOH, and that would be an acid group. And here, if you just look at this, you have a CO and N and R, RCON, which is exactly like this, but it has also another R. So this is representing this area that is also an amide, but it is in cyclic form, cyclical amide. And in this third problem, you have an amine, RNH2, this is amine, but it's primary. And this one right there is an acid, represented as COOH. And here you have functional group like this is a triple bond, it's an alkyne. You have an alkene, double bond. Similarly, you have an alkene and alkyne, but here you have an amine group, which is secondary amine, and here you have an alcohol. So basically, these are the functional groups presented in this four compounds. Okay, continuing our discussion on still on functional groups. These are all of them are cyclic functional groups. For example, in compound A, you'd see in nitrogen, which is an amine, but in a cyclic form, you have R, another R, and R. So this is in between 3 carbon groups around the nitrogen, but it is a cyclic one. Still, it is an amine functional group, and the amine is a tertiary amine because the nitrogen is attached to 3 different carbons: this carbon, that carbon, and that carbon. Therefore, it is a tertiary amine. Tertiary amine. In the next one, you see a compound B. You have a 5-member ring, but one of them is replaced by oxygen. So this is an ether because R, O, R prime. That means whenever you have a oxygen bridging 2 R groups, that would be a cyclic ether. So that is a cyclic ether compound. In compound C, what you see is R, one side, CO, O, another R. So in functionality wise, this is an ester because it has R, CO, O, R prime, a different R. For the ether, it is R, O, R prime. That's an ether. Here, the amine is represented as R, 1, 2, N. That is a tertiary amine because there is R from this side, another R, and another R, the alkyl groups. So that's a tertiary amine in general. So esters, which are in a cyclic form, are called lactones. So this is a special name for general esters that are in a cyclic form. They are called lactones. Here you see also an amide. It's amide because you have R, CO, N, H, R. So in general, this is R, CO, N, H, R prime. So this is an amide, which is in a cyclic form. They are called lactams. They are amide, but special amides where they are in a cyclic form. So these are called lactams. For esters, the cyclic form are called lactones. So this is just a general review of some of the cyclic compounds that have heterofunctional groups in them. This problem, we are asked to rank them according to the strength of the intermolecular forces between compound A, B, and C. Now, we should identify first what intermolecular force that possibly exist in these compounds. For example, compound A can only have most of weak van der Waals or dispersion force. As you see, there is no any heteroatoms that can make hydrogen bonding. There is no dipole that is possible for dipole-dipole interaction. So the only force that exists in this compound is van der Waals forces. In compound B, of course, van der Waals force exists, that plus. In addition to that, as you see, this is a carboxylic acid. That's the functional. This is an alkene compound. So, together with the van der Waals force, there is also hydrogen bonding. So, it benefits from 2 forces that are playing into the intermolecular forces. Remember, these structures are closely related in the number of carbons they have. They are not exactly the same, but they are similar in order to compare them. This functional group here is the R is this OR, that is an ether functional group. Ethers usually they cannot make hydrogen bonding, but there might be a weak, obviously there is a van der Waals forces for this compound. In addition to that, there might be a very weak dipole might exist. Weak. So when we compare all this and rank them according to the strengths, B is the greatest. B is much greater than C and much greater than A. So the weakest intermolecular forces, I would say, would be in compound A, which is just an alkene, but compound B has hydrogen bonding plus van der Waals forces and hydrogen bonding through this OH. This functional group is an acid. Acids usually make a hydrogen bonding, and they would have the greatest intermolecular force for this comparison. So the dipole might be, because of the oxygen, might pull some electron density like this, and also pull some electron density like this, and this may not be a linear molecule. It might have a bent shape that could totally add up some dipole in that direction. Because of that, that ether might have an induced dipole interaction. Therefore, in the ranking, B is the strongest intermolecular force, strongest, and A would be the weakest intermolecular force. Intermolecular force, strongest intermolecular force. So that's how we rank them for this problem. Here we have 4 compounds to compare their boiling point and arrange them according to increasing order of their boiling point. As you know, boiling point depends on the intermolecular forces that exist within the molecule. Here, first let's identify what kind of intermolecular force exists. The intermolecular force mainly for compound A is van der Waals forces or dispersion, which is the weakest intermolecular force. Of course, all of them would have van der Waals dispersion forces. Van der Waals or dispersion forces. These are based on the chain. Here also van der Waals dispersion forces. But if you just look at the chain lengths, here we have a 5 carbon length, which is C5H12. Here we have 4 carbon, but you have oxygen, so in terms of dispersion forces, they would be comparable. So this is a C4H9OH, I believe. 3, 5, 7, 9, 10O, C4H10O compound. This is a 1, 2, 3, 4, which is a C4H9Br compound. Here we have a C5H12O, which is 3, 5, 7, 9, 11, 12. So in terms of dispersion, C5 and this compound and this compound might have almost comparable dispersion forces. Now, if we just look at compound B, it has additional, because of the alcohol functionality, alcohol, it would have hydrogen bonding. And if you just look at this one also, which has an alcohol, it has hydrogen bonding as well. And if you come to this compound right here, because of the CBr dipole moment, because the electronegativity difference between carbon and bromine, it would induce a dipole where it is sigma plus and sigma minus. Therefore, this would have a dipole force. Now, when we come to arranging in the order of increasing their boiling point, the highest boiling point would be because of compound D. Compound D has dispersion force as well as hydrogen bond. But how does it differ from this? It has a dispersion and also hydrogen bond. The difference here is the chain length. The chain length here is 5 carbon chain. Here the chain is 4 carbon. So dispersion force is higher whenever you have higher length of the chain. So you have 1, 2, 3, 4, 5 carbon, a 5 carbon chain. Here you have only 4 carbon. So the dispersive force of D is higher than the dispersive force of B, even though the hydrogen bonding between the two is equal. So the strongest or the highest boiling point compound would be D. D is greater than, obviously, B, because, as I said, the dispersive force in compound D is higher because the chain length is 5 carbon lengths as compared to a 4 carbon. That's why D has the highest boiling point, but the next followed by B, which is hydrogen bonding and also dispersive force. Next one would be a dipole interaction, which is next to that would be compound C, and the lowest boiling point is compound A. So this is the order of boiling point. This is lowest boiling point in temperature because of the differences in intermolecular forces. Here in this problem we have 2 compounds, vitamin B6, which is called pyridoxine, and vitamin E from the left side. So the question is, which one do you think, based on the molecular structure and based on the functional groups that are in the molecules, which one do you think is more water soluble? So in order for you to identify water solubility, most of the time compounds that are polar dissolves in polar. Compounds that are hydrophobic or just hydrocarbons without any heteroatom mostly dissolves in organic or non-polar solvents. So if you just look at the structure of these 2 compounds, vitamin E and vitamin B6, there is greatly a functional group difference what is seen in this. So as you see, it's a long chain of aliphatic compound. When we say aliphatic compound, it means just carbon, hydrogen, which are mostly non-polar. So this chain is very long, and most of it is just hydrocarbon. Hydrocarbons, they don't dissolve easily in water because they are hydrophobic. The only one possible heteroatom that exists in vitamin E is just only this one hydroxy group. Obviously, that hydroxy group can make a hydrogen bonding with water. But as you see, most of the molecule, most of the compound is hydrophobic. So it is very unlikely that the vitamin E is soluble in water. So as you know, vitamin E is not actually soluble in water. But unlike vitamin E, if you just look at this compound, a compact molecule, it has 3 hydroxy groups that can make hydrogen bond with water, like this. That hydrogen would make a hydrogen bonding. That hydrogen can make also another hydrogen bonding. That hydrogen also can make a hydrogen bond with water molecule. And even nitrogen with its lone pair has also a certain level of dipole. So if you just compare the 2 compounds, this compound could be said as polar. Polar compound, since water is a polar molecule as well, and vitamin B6 is a polar molecule, so it is more soluble. So vitamin B6, based on the functional group, it has a more polar hydroxy compound, would be more soluble in water, while vitamin E, which is hydrophobic, because of long chain of hydrocarbon, it is non-polar and not soluble in water. So when you take vitamin E versus vitamin B6, the vitamin B6, you can take a large dose amount of vitamin B6. Since it is water soluble, it will be excreted easily. But if you take vitamin E, it might overdose on vitamin E. Most likely it could cause also some toxicity because it's not very soluble in water and very hard to remove from our body or eliminated through our urine. So that's the difference between these 2 compounds. Because of the functionality or the functional groups on vitamin B6, which can make several hydrogen bonding, it becomes a more polar compound and soluble in water. A hydrophobic compound, this is very hydrophilic. This is a hydrophobic compound with a long chain of hydrocarbon. This is the chain of hydrocarbon chain. That makes it a hydrophobic compound. Therefore, vitamin E is not soluble in water as compared to pyridoxine, which is vitamin B6.